This is part of a series I call the Making Evidence-Based Medicine Simple series, or MESS for short. In MESS Minis, we review an essential evidence-based medicine concept. In this MESS Mini, we will discuss sample size determination. The terms sample size determination and power analysis are sometimes used interchangeably. I prefer the term sample size determination because we are most often setting the desired level of power and solving for the sample size. Hypothesis testing and sample size determination use similar formulas to answer different questions. In hypothesis testing, we input the statistical test, the hypothesis type, whether the alternative hypothesis is one or two-sided, and the desired alpha error. The sample size and difference between the groups is calculated from the data provided. Hypothesis testing yields the level of alpha error in the form of a p-value, the likelihood of concluding there is a difference when there is no difference. In sample size determination, we input the statistical test, the hypothesis type, whether the alternative hypothesis is one or two-sided, and the desired alpha error, beta error, and effect size. The desired effect size is equivalent to the difference between groups in hypothesis testing. Sample size determination yields a sample size. This slide illustrates the steps in sample size determination. We will review each of these. Step 1 is stating the null and alternative hypothesis and specifying if the alternative hypothesis is one or two-sided. Unless otherwise specified when discussing hypothesis testing, we will use a superiority hypothesis since it is the most common hypothesis type. This is the null hypothesis for superiority hypothesis. The null hypothesis is determined prior to any analysis to avoid the appearance of data dredging. The null hypothesis is the hypothesis of no difference and the hypothesis that is tested. If we reject the null hypothesis, there is a statistically significant difference. If you fail to reject the null hypothesis, there is not a statistically significant difference. The phrase fail to reject the null hypothesis is a bit cumbersome, but the term accept the null hypothesis is frowned upon by statisticians. This is the alternative hypothesis for a superiority hypothesis. The alternative hypothesis is the complement of the null hypothesis. The alternative hypothesis is typically the research hypothesis and is the hypothesis of a difference. The alternative hypothesis is a hypothesis that is accepted if you reject the null hypothesis, and is a hypothesis that is rejected if you fail to reject the null hypothesis. The direction of the alternative hypothesis, whether it is one-tailed or two-tailed, must be specified. A two-tailed hypothesis indicates there is a possible difference in either direction. That means the possibility exists that A can be superior to B and that B can be superior to A. A two-tailed hypothesis is more conservative and commonly used. A two-tailed hypothesis should be used unless there is a clear reason not to use it. Note that both tails of the typical alpha error of 5% are divided by 2, resulting in two tails of 0.25 or 2.5%. In contrast, a one-tailed hypothesis indicates that a difference is possible in only one direction. A can be superior to B, but B cannot be superior to A. Note that the area of rejection of the null hypothesis is 0.05 or 5%. This differs from the 0.025 or 2.5% on either side of the two-tailed hypothesis and results in a greater power to find a difference with one-tailed hypothesis. A one-tailed hypothesis should only be used when the difference is only possible in one direction. This is rare, and for a non-inferiority hypothesis. Step 2 in sample size determination is identifying the type of alternative hypothesis. This slide illustrates the three hypothesis types: superiority, equivalence, and non-inferiority. It is helpful to remember that each of the hypothesis types are named for their alternative hypothesis. When comparing two groups, one group can be the same, better, or worse than the other group. The red portion of the arrow indicates the alternative hypothesis, and the gray portion of the arrows indicate the null hypothesis. The difference in a superiority hypothesis is called the effect size. The difference in an equivalence hypothesis is called the equivalence margin, and the difference in a non-inferiority hypothesis is called the non-inferiority limit. Step 3 in sample size determination is choosing an appropriate statistical test. Selecting a statistical test is based on several factors. The following questions should be answered. Is the purpose of the analysis to describe the data or to make inferences from the data? Do you want a test that provides a qualitative measure of association, a p-value only, or a quantitative magnitude of association, for example, a numeric correlation coefficient? What type of data is the dependent variable? Is it nominal, ordinal, or continuous? What type of data are the independent variables? Are they nominal, ordinal, or continuous? How many independent variables are being compared to the dependent variable? Is this a univariable, bivariable, or a multivariable analysis? And are there assumptions of the selected test that must be fulfilled? For example, parametric statistical tests require that the groups be normally distributed. Step 4 in sample size determination is choosing the effect size. This is the most challenging step because it is often a matter of judgment. We will use an effect size for a superiority hypothesis as an example. The effect size is the minimal clinically significant difference that would change clinical practice. Essentially, sample size determination provides the number of patients needed so that if the difference is clinically significant, then it is statistically significant as well. Sometimes the literature will be helpful in defining the effect size. For example, the effect size for a clinically significant difference for a visual analog pain scale is generally considered to be 13 millimeters, or 1.3 centimeters. Other times, a pilot study may be required to determine the effect size. Choosing an effect size is often a matter of judgment on what constitutes clinical significance. Sometimes it is an educated guess that needs to be reevaluated when data becomes available and may require redetermining the sample size. The take-home message is that the smaller the effect size, the larger the sample size required. Calculation of the effect size is dependent on the type of data. For categorical data, when comparing two proportions, the effect size is simply the difference between the two proportions. For continuous data, when comparing two means, the effect size is the difference between the two means divided by the standard deviation. Step 5 in sample size determination is choosing the acceptable levels of alpha and beta error. When we reject the null hypothesis, and there is a statistically significant difference, there are two possibilities. We can correctly reject the null hypothesis, and we can erroneously reject the null hypothesis. Power is the probability of correctly rejecting the null hypothesis. Alternatively, power is the probability of concluding there is a difference when there is a difference. An acceptable level of power is typically 80%. Power is 1 minus the beta error. Therefore, selecting a power of 80% corresponds to a beta error of 20%. An alpha error is also called a type 1 error and is expressed by a p-value. An alpha error is a probability of erroneously rejecting the null hypothesis. Alternatively, an alpha error is the probability of concluding there is a difference when there is no difference. We have somewhat arbitrarily set a standard probability of an alpha error to be acceptable at a level of less than 0.05 or 5%. This can be thought of as a less than 5% or 1 in 20 chance that there is no difference when we conclude there is a difference. For a p-value of less than 0.05, we reject the null hypothesis and conclude there is a statistically significant difference. For a p-value greater than or equal to 0.05, we fail to reject the null hypothesis and conclude there is no statistically significant difference. When we fail to reject the null hypothesis, there are two possibilities. We can correctly fail to reject the null hypothesis, and we can erroneously fail to reject the null hypothesis. 1 minus alpha is the probability of correctly failing to reject the null hypothesis. Alternatively, 1 minus alpha is the probability of concluding there is no difference when there is no difference. If the probability of an alpha error is 0.05 or 5%, then the probability of 1 minus alpha is 0.95 or 95%. A beta error is the probability of erroneously failing to reject the null hypothesis. Alternatively, a beta error is the probability of concluding there is no difference when there is a difference. Again, we have somewhat arbitrarily set a standard probability of a beta error to be acceptable at 0.2 or 20%. Notice that we are willing to accept a higher level of beta error, 20%, than alpha error, 5%. If the probability of a beta error is 0.2 or 20%, then power, which is 1 minus beta, is 0.8 or 80%. This 2x2 table summarizes the conclusions that can be made with hypothesis testing. The columns represent the truth, whether there is a difference or no difference. The rows represent the conclusions made in either rejecting the null hypothesis or failing to reject the null hypothesis. In this table, the green bordered cells indicate areas of concordance. This is when there is an agreement between the conclusion regarding rejecting or failing to reject the null hypothesis and the truth. The upper left-hand cell represents power, which is the probability of correctly concluding there is a difference when a true difference exists. Unfortunately, the lower right-hand cell doesn't have an interesting name, but I will call it 1 minus alpha. In this cell, we correctly conclude there is no difference when no true difference exists. In this table, the red bordered cells indicate areas of discordance or error. An error occurs when there is discordance between the conclusions made to reject or fail to reject the null hypothesis and the truth. An alpha error occurs when we erroneously conclude that there is a difference when there is no difference. A beta error occurs when we erroneously conclude that there is no difference when there is a difference. In this table, the correct and erroneous conclusions are expressed as probabilities. In the right upper cell, we typically accept an alpha error probability of 0.05 or 5%. This corresponds to a p-value of less than 0.05. There is a 5% probability of concluding there is a difference when there is no difference. If there is a 5% probability of concluding there is a difference when there is no difference, then there is a 95% probability of concluding there is no difference when there is no difference. This corresponds to the 95% in the 1 minus alpha cell. In the lower left cell, we typically accept a probability of beta error of 0.2 or 20%. There is a 20% probability of concluding there is no difference when there is a difference. If there is a 20% probability of concluding that there is no difference when there is a difference, then there is an 80% probability of concluding that there is a difference when there is a difference. A beta error of 20% corresponds to a power of 80%. Power is the probability of concluding there is a difference when there is a difference. These are the typical values used in most studies: an alpha error of 0.05 or 5% and a beta error of 0.2 or 20%. Since power is 1 minus the beta error, a 20% beta error corresponds to 80% power. As I've indicated before, these have been somewhat arbitrarily chosen. The last step in sample size determination is calculating the sample size. There are several software options for this. The major statistical analysis programs like SPSS have a sample size determination module. Two free options are GPower, which is available for both PC and Mac, and the website sealedenvelope.com. This is an example of the sealedenvelope.com website for sample size determination of two proportions with a superiority hypothesis. We input our proportions, the level of alpha error, and power, and click on Calculate Sample Size. The effect size is the difference between the two proportions. 90% minus 75% equals 15%. The output indicates that we would need 97 patients in each group for a total sample size of 194 patients. One benefit of using sealedenvelope.com is that you can calculate sample size for a superiority, equivalence, and non-inferiority hypothesis. The second benefit is that it gives you a sentence to add to the statistical analysis section of your research protocol. If there is insufficient power or too large a sample size, consider modifying the hypothesis. Use continuous data and a parametric statistical test that provides a smaller sample size for a given power. Use a paired statistical test if appropriate. Paired tests have less variability and greater power to find the difference. Use more precise measurements. Less variability results in greater power. If there is insufficient power or too large a sample size, consider modifying the assumptions used in determining the sample size. Is the effect size too small? Is the variability too large for continuous data? Are the selected alpha and beta errors too low? Would a one-side alternative hypothesis be appropriate? In summary, sample size determination and hypothesis testing use the same concepts to solve for different outcomes. Hypothesis testing solves for the level of alpha error or p-value. Sample size determination solves for n, sample size. Sample size determination requires several steps. These include stating the null and alternative hypothesis and whether the alternative hypothesis is two-tailed or one-tailed, identifying the alternative hypothesis type, superiority, equivalence, or non-inferiority, choosing an appropriate statistical test, choosing the effect size. This is often the most challenging step as it requires judgment. Choosing the acceptable levels of alpha and beta error. Typically, this is 5% for alpha error and 20% for beta error. A 20% beta error corresponds to 80% power. And final step, calculating the sample size using statistical software.